Hey guys, this is Anne. So in this video, I'm going to give you guys an introduction to number systems. So specifically base 10, base 2, base 16, and base 8. If you want to see how to convert one system to another or one base to another, you can check out my other videos. I also have some videos on how to perform arithmetic operations in different bases. So, for example, adding and subtracting in base 2, you can check out the video as well. So let's start with base 10. So base 10 is what we usually use in math. So most numbers you see in your daily life is in base 10. So it says here, any integer can be represented uniquely as a sum of the products of the form d times 10 to the nth power, with n being an integer and d being a decimal digit. So it could be 0, 1, 2, 3, 4, 5, 6, 7, 8, or 9. And so let's give the example of 3,957. I'm going to put a subscript 10 just to indicate that this number is in base 10. Now this number is equal to 3,000 plus 900 plus 50 plus 7. And that is equal to 3 times 1,000 plus 9 times 100 plus 5 times 10 plus 7 times 1. And that is equal to 3 times 10 to the third power plus 9 times 10 to the second power plus 5 times 10 to the first power plus 7 times 10 to the 0th power. So now, as you can see, we have products, and the sum of these products equals 3,957. So these products are in the form of d times 10 to the nth power. In this case, d is equal to 3. 10 to the third power means n is equal to 3. Over here, d is equal to 9. N is equal to 2. Over here, d equals 5. N equals 1. And over here, d equals 7. And n equals 0. In order to form the base 10 number, what we do is we take all of the d's. So 3, 9, 5, and 7. We write that down. And because 3, 9, 5, 7 can be written in this form with d being decimal digits and n being integers with 10 to the nth power, we know that this number right here is in base 10. Okay, now let's look at base 2. Any integer can be represented uniquely as a sum of the products of the form d times 2 to the nth power. So n is an integer, and d is equal to binary digits. So d can either be 0 or 1. So let's say, for example, we have the number 209 in base 10. When we rewrite this number so that it's the sum of the products in the form d times 2 to the nth power, we get this equation right here. And now, in order to rewrite 209 base 10 into base 2, we just take all the d's. So the d's are 1, 1, 0, 1, 0, 0, 0, 1. And then we put a subscript 2 to indicate that this number is in base 2. And there you have it. 209 in base 10 is equal to 110100001 in base 2. I took d times whatever base it's in to the nth power. So in this case, it's 10 to the nth power since it's base 10. And here it's 2 to the nth power since it's base 2. And I can know what the possible options of d is by taking 10, subtracting 1, and I know that 10 minus 1 is 9, so the possible decimal digits are 0 through 9. And here, for base 2, I take 2, subtract 1, so 2 minus 1 is 1. So I know the binary digits are from 0 to 1, so just two options, 0 or 1. Okay, now let's look at hexadecimal. So hexadecimal is the same thing as saying base 16. Again, any integer can be represented uniquely as a sum of the products of the form d times 16 to the nth power. So in order to know what the possible D options are, I take 16, since this is base 16, and then I subtract 1. 16 minus 1 is 15. So the hexadecimal digits should be from 0 to 15. A is actually representing 10, B is representing 11, C is representing 12, D is representing 13, E is representing 14, and F is representing 15. So let's say we have the number 3,957, base 10, and I want to rewrite this number as the sum of the products in the form d times 16 to the nth power. So I'm not going to explain how I converted a decimal number into a hexadecimal number in this video. So I'm just going to write the equation, since this is just an intro video. So I was able to rewrite this number into an equation where if I add these products up, I get this number, and now I have to collect the D's. Well, the problem is if I write 15, 7, and 5, the 15 looks like 1, 5. So it looks like I'm writing 1, 5, 7, 5. But I'm actually writing 15, 7, 5. So this is confusing. So instead of writing 15, I would write F, and then 7, and then 5. And there's no issue with 7 and 5 since they're just one digit. And then I'm going to write the subscript 16 just to indicate that this is base 16. So 3,957 in base 10 is equal to F75 base 16. Okay, now let's look at octal notation, aka base 8. So any integer can be represented uniquely as a sum of the products of the form d times 8 to the nth power. N is an integer, and D have a couple options. In order for me to figure out those possible options, I take 8, since we're dealing with base 8, subtract 1 from it, so 8 minus 1 is 7, and so the possible D options are 0 through 7. So let's deal with 3,957 in base 10 again. I'm going to rewrite that as 7 times 8 to the third power, plus 5 times 8 to the second power, plus 6 times 8 to the first power, plus 5 times 8 to the 0th power. So now, these products are in the form d times 8 to the nth power. If I add them all up, I get 3,957. So in order to get the base 8 number, I would take all the d's. So they would be 7, 5, 6, and 5. And I will put a subscript 8 right here to indicate that this number is in base 8. And there you have it. 3,957 in base 10 is equal to 7,565 in base 8.